So thanks a lot for inviting me. And yeah, so remember, if you have any questions, yeah, then put them in the chat. Yeah, and at the end, yeah, I can answer whatever you have. Yeah, if you have questions, yeah, after the presentation, like I don't know, next week, yeah, you can send me emails, yes, or write on the Discord. Okay, so let's start, yeah, by roughly recalling what is full homomorphic encryption. So it is a very special type of encryption scheme where a user can encrypt a message M and send the ciphertext to a server. And now the server, without any special secret key, can compute an arbitrary function on F on the ciphertext. And then it sends the result of the evaluation back to the user who can decrypt F from F. That is the result of applying the function F on the encrypted message M. And importantly, the server doesn't learn the message M because it's encrypted. Now, FHE has numerous applications that many of you already know. For instance, inference on genomic or medical data, or any other data, really, like your emails or pictures. And a popular application is private information retrieval, where we query a database without revealing the content of our query. But importantly, with just FHE alone, we protect only the data from the user on the left, and we don't protect the computation from the server. Okay, so let's recall the formal definition. So an FHE scheme will consist of 4 algorithms, and that is setup, that outputs a secret key and a public key, encryption, that on input the public key and a message outputs a ciphertext. Then we have decryption, that on input a secret key and the ciphertext outputs a message, and evaluation, that on input a function F and a bunch of ciphertexts outputs a ciphertext. And then we say that the FHE scheme is correct if the probability that eval returns something other than F from M1 to Mn, given ciphertexts that decrypt to this MIs, is negligible. Okay, then for compactness, we require that the size of the outcome of the evaluation doesn't depend on the size of the circle. And finally, we define NCPA security in the usual way. So we have an adversary that chooses 2 messages, and the challenger encrypts one of these messages, and the adversary must guess which message was encrypted. So to remind that FHE does not protect the data or computation done by the server. So for example, if we evaluate neural networks, or we query a database, we want it on an encrypted query. Like in these previous applications that we talked about. So this database, or these neural networks may actually leak. So the point in FHE so far was actually delegation. So if we don't want to do computation locally, but we prefer that a server does it slower over encrypted data, then we can use FHE. One good thing, however, is that the server doesn't have to send the database or the neural networks to the clients. So communication may be smaller. Now, to see that there is information leak when computing on encrypted data, so note that the evaluation algorithm is usually deterministic. So just think of the following attack, where the client guesses a function F, runs evaluation locally, and checks if the local computation matches the server's output. So with a high probability, the ciphertext will match if the guessed function F is the same as the function computed by the server. And note that this is just an example attack. and it's here to show you just that this information leakage is present. So maybe much more information about the computation leaks through the output ciphertext. So who knows? But to prevent any information leakage, we can equip FHE with an additional property that is called circuit privacy. And in the literature, it is sometimes called function privacy. We can rebrand it to program privacy, so whatever you want. Okay, so informally, we can define circuit privacy such that we have an adversary that holds the secret key of the FHE scheme. And the job of the adversary is to guess whether it obtains responses on its ciphertext from the real evaluation algorithm that you see on the left, or from a simulator that gets as input only the outcome of the computation, so F from M and the public key. But in particular, the simulator has no additional knowledge on the function F. And now, if the adversary cannot distinguish between these two words, then we say that the FHE scheme is circuit private. In other words, the output ciphertext Cout don't leak any information on the function F. So in this paper, I'll show you how to build FHEW/TFHE-Style FHE scheme with circuit privacy. Okay, so let's get back here to our applications. So now with circuit privacy, we can run inference on genomic data or medical data, analyze pictures or emails, but without revealing any information on the server's computation. So, and in cryptography, for example, there are immediate applications, and for example, oblivious pseudorandom functions, where our server evaluates our PRF on a user message without learning the message. But on the other hand, yeah, the user doesn't learn any information about the secret seed S. And similarly, we can do with blind signatures. Yeah, so the user message is encrypted and the server's secret signing key doesn't leak. But to summarize, we get semi-honest secure two-party computation, and that is we can compute any function without revealing the inputs of both parties, or even we can hide the function F that is computed by the server. So what else do you want? And interestingly, so some recent works showed that circuit private FHE gives you FHE that satisfies some relaxed variants of CCA2 security. So that's something to check out. And okay, so at this point, let's make a short pause and let's answer some frequently asked questions. Yeah, or address some myths. Yeah, that I at least noticed circle around the internet. And question number one is, does computing a universal circuit give us circuit privacy? And the answer is no. And why? Is that so note that the adversary can launch exactly the same attack as we discussed earlier and simply test on whether a circuit was evaluated by running locally the same universal circuit. So I think that this misconception, that universal circuits give you that evaluating a universal circuit gives you circuit privacy came from the garbled circuits literature. Because for garbled circuits, it's indeed computing a universal circuit is a technique to hide the topology of the garbled circuit. But in FHE, evaluating garbled universal circuits does really nothing for circuit privacy. Question number two, does adding a freshly sampled ciphertext of 0 give us circuit privacy? And the answer is that it depends. So there are indeed linearly homomorphic encryption schemes like LGAML, for example, where it is going to work, but for LWE-based schemes, which are noisy, this noise may depend on the computation. And unfortunately, just adding a fresh LWE sample of 0 is not going to sanitize the noise terms. Question number three. does multi-key FHE give us circuit privacy? And so here the idea is that we encrypt the circuit and compute on the encrypted circuit and return a partial decryption. And now, because the circuit is encrypted, there is a belief that that this should give us circuit privacy. And the answer to this question is actually complicated. To the point that with Giacomo Santato, we wrote a paper about it. And it seems that the fact of encrypting the circuit itself doesn't really help at all in terms of circuit privacy. So what helps is flooding the noise in partial decryption. And we can do noise flooding like even without multi-key computation. So encrypting the circuit doesn't seem to help much. Question number 4. If I homomorphically evaluate a neural network without circuit privacy, does my entire model leak? And the answer to that is that it doesn't always look easier to extract the entire computation, and perhaps it's not even possible. But stealing the entire computation, or like the neural network, is not always the goal of the adversary. So sometimes it's enough that the adversary learns that a particular neural network was used by the server. Sometimes 1 bit leakage per, I don't know, 500 queries is enough to eventually extract a secret key. But in general, we aren't able yet to foresee what kind of future attacks in all the possible applications can exploit the lack of circuit privacy. So the idea is that I want to make circuit privacy the default option so that we don't even have to think about this. And this is circuit privacy by default is really what motivates this work. Okay, so to summarize my contributions towards providing circuit privacy by default is that I designed a sanitization algorithm that is based on FHEW, TFHE-Style bootstrapping algorithms, and I proved its security. In short, to sanitize a ciphertext from any information about the circuit, you only need to invoke one bootstrapping step before returning the ciphertext. And along the way, so I generalized some technical lemmas from previous work. And then I implemented the scheme and some schemes from previous work. So actually, when it comes to implementation, there is a lot to talk about because it comes with different arithmetic backends. So you can choose, for instance, to compute on floating point numbers and multiply polynomials with fast Fourier transforms, or you can compute on finite fields using the number theoretic transform. Then different arithmetic backends give us different possibilities for choosing our parameters, and there are different trade-offs between all of these options. Then I came up with a few optimizations, so that deterministic computation is as fast as non-circuit private FHE, but without publishing additional bootstrapping or key switching keys. And there are also some Python scripts to estimate and partially generate circuit private FHE parameters. And third, so I revisited the work from Duca and Still from 2016. And so I thought that this was their state of the art when it comes to circuit privacy. In short, so I revisited the parameters that they suggested. I gave a serious analysis of these parameters and included their method into my estimator scripts. And finally, so the method is implemented, and all that was just for the sake of comparison. And finally, so everything is available in a new C++ library that I call FHE-Deck. And the main promise is to offer this FHE with circuit privacy by default. All right, so let's finally talk about some algorithms and how to get circuit privacy for FHE. So let's start with the idea of adding a freshly chosen ciphertext of 0 to a WE ciphertext. So remind that a WE ciphertext consists of a vector A and integer B. that is the inner product between the A vector and a secret key vector S, the message M, and a small arrow E. Okay, so now we will add to this fresh ciphertext of 0. And at first glance, yeah, it looks good. Yeah, so the vector A out will actually be uniformly distributed, but the arrow E fresh is unfortunately too small. You have to sanitize all the information about the previous computation from the arrow E. So idea number 2 is the same as earlier, but this time let's add a huge arrow term E to the ciphertext. So now this technique is called noise flooding, or sometimes people call it drowning. And the problem with that is that the size of the flooding error must be exponential in the security parameter to sanitize the ciphertext noise. So in practice, this means that we need to increase the ciphertext modulus by over 80 bits, and consequently, we lose security. And to compensate, we need larger dimensions for our LWE or RIN LWE instances. And at least to the best of my knowledge, no one ever implemented something like this for FHEW or TFHE-Style full homomorphic encryption scheme. And I think there are good reasons for that. Yeah, so namely, at least intuitively, like the efficiency of those schemes would collapse. Yeah, so why the schemes are so efficient is that the parameters are relatively low. Okay, so idea number 3 is to use smaller flooding noises to keep the parameters relatively unchanged. And then let's bootstrap and apply this small noise flooding repeatedly in a loop. And this idea was actually introduced by Duka and Stiel at Crypto 2016. And so I was calling it Duka Stiel washing machine. Yeah, so due to this washing cycles that we perform. And in their paper, so they proposed to run a FHEW bootstrap for 8 to 16 times. So the downside of this method is obviously that we need to run bootstrapping many times. And bootstrapping is in itself relatively expensive. But also they left a serious analysis of their parameter choice for future work. So in this work, I actually do this serious analysis, and compare this to my idea. So finally, my idea was to build a special randomized bootstrapping algorithm that with just one bootstrapping invocation sanitizes a ciphertext from all information on the previous computation. So next, I will show you the very high-level idea on how such a bootstrapping algorithm works. And so at the core of FHEW TFHE-Style bootstrapping algorithm is a procedure called blind rotation. So this blind rotation takes as input our LWE sample, and that is a vector A and an integer B, and a ring element CACC. So this is an accumulator, or sometimes called rotation polynomial. And the blind rotation algorithm outputs a ring LWE ciphertext that encrypts this rotation polynomial CACC multiplied by X to the linear decryption of the LWE ciphertext. Then the next step in bootstrapping is to take this ring LWE ciphertext and extract our LWE sample that encodes the constant coefficient of the ring LWE ciphertext's message. So long story short, if the computation is correct, this LWE ciphertext is simply a LWE encryption of F from M. So it doesn't really matter in this talk why this works. So there was a lot of talks that explained this previously. So what matters is that okay, so if everything is correct, then at the end of this process, we get a LWE ciphertext of F from M. Okay, so let's denote this LWE ciphertext as A X and B X. And Bx, yeah, is the inner product of the Ax vector and the secret key S plus F from M plus the error term Ex. So now to sanitize this ciphertext, the first step here will be to add the ciphertext of 0 to it. And let's say that we add A fresh and B fresh. And now remind that as earlier, we have that the output vector, A out, is uniformly distributed, assuming A fresh is uniform. But as earlier, the error term Ex still leaks information on the computation. Yeah. So this E fresh is too small. You have to sanitize the final error. So what can we do? So let's now have a little bit closer look at the blind rotation algorithm. So this is a super simplified description, but in general, blind rotation starts with a ring LWE ciphertext called the accumulator, and then it consists of a sequence of ring LWE and ring GSW products, and finally we return the ring LWE ciphertext CT. But most importantly is that at the heart of this products is a decomposition algorithm, G to the -1, that takes ring LWE as inputs and outputs a vector of ring elements, this DJs, of small norm. So in practice, most implementations use a deterministic digit decomposition algorithm. So something like a binary decomposition, but generalized to larger digits. Now we can prove that the final error of the ring LWE ciphertext CT is a linear function between this DJ's polynomial and the error terms of the ring GSW ciphertext here denoted as EJs. Okay. Then the next step is that we can show that in this specific ring that we are working in, the extracted LWE ciphertext has its error in the form of this inner product of the individual coefficients of the DJ polynomials and the coefficients of the ring GSW errors. Yeah, so actually in the paper, the proof of why the error is in this form takes, I believe, like two pages. Yeah, so in the talk, yeah, so you just have to believe that it is like that. Okay, so now the idea to sanitize this error is to take a very special randomized digit decomposition algorithm instead of this deterministic one. So these algorithms work just like a normal digit decomposition algorithm. So our computation remains correct, but the outputs, these DJ polynomials, have coefficients, for instance, from the Gaussian distribution. And now, finally, with this randomized decomposition algorithm, we can prove that the resulting noise is statistically close to an independent random variable. Importantly, like independent from the function f. Okay, so to summarize, we first get that A out is uniform because we add a fresh LWE sample to the extracted ciphertext. And then we get that the error term is independent due to the use of this special randomized decomposition algorithms. And finally, so note that this error term E fresh was never dependent on the function f, so we don't really have to care about it. So to let it all sink in, let's briefly go through the security proof. So at the beginning, we start with this LWE ciphertext that has its B out of the form as you see on the slide. Then we show that the error term Ex is indeed in this linear function of the random DKs and the error coefficients from the ring GSW ciphertexts. Then we need to assume that the computation is actually correct. So, and this comes from the assumption that the FHE computation was was correct. Okay. The next step is that we have that A out is uniform if A fresh is uniform, and this comes from the leftover hash lemma. So we actually sample this fresh ciphertext by computing a random multi-sum of LWE ciphertext of 0. And then we need the leftover hash lemma to argue that the samples are freshly looking, so that they are distributed like a fresh LWE sample. The last step is to argue that the noise is close to an independent discrete Gaussian random variable, and this is shown by a generalized Gaussian leftover hash lemma. And the lemma was actually first introduced in a paper from 2016, but they needed a special modulus. So in my paper, I generalized this to arbitrary modulus. And okay, so this was like the last mathematical slide. So now we can get finally to implementation. So the security targets for the parameters and the experiments is 128-bit of computational security for int CPA, and 80 bits of statistical security for secret privacy. And now note that 80 bits is usually enough for statistical security, and this is because the security is actually the statistical distance between random variables. And in particular, so the security, statistical security does not degrade in the future with new attacks, advances in computational power and so on. So usually with statistical security we can be a little bit more relaxed when taking the security parameter, but with computational security it's better not to be so relaxed. So we take 128. Okay, so to meet these requirements, I chose a ring that has like dimension equal to 2 to the 11, and to compare my method with the current state of the art, and that is the current field washing machine method. But remind that I actually came up with new parameters because the previous didn't really meet the security goals. And I think that my parameter selection is even faster. And this is because we don't. It turns out that we didn't need so many bootstrapping repetitions. Okay, then there are actually two implementations or like two backends for both methods. So 4 parameter sets in total. One implementation is on integers modulo a prime number, and it uses the number theoretic transform from Intel Hexel for polynomial multiplication. And then the other one is a 40-bit, 64-bit double precision floating point number based implementation with fast Fourier transforms from the FFTW library. Then the parameters for each implementation are chosen such that the bootstrapping keys for my scheme and DS16 are the same, and both schemes can be run in 2 modes. So the deterministic mode and the simulation mode. So in the simulation mode we sanitize a ciphertext, but the deterministic mode we choose the parameters so that to allow computation as fast as possible, but the ciphertexts are not sanitized in this mode. So both modes use the same bootstrapping key BK, so you don't need to publish any new bootstrapping keys or any new key switching keys or something like that. And the difference in the efficiency you can already see in the last columns. So mul det and mul sim. So this gives you the number of polynomial multiplications in ring LWE and ring GSW products in the deterministic and simulation modes. Now, both implementations have some pros and cons. So the NTT, for instance, can use a larger modulus, and therefore we can perform fewer multiplications per ring LWE and ring GSW product. For floating point number implementation, we need a smaller modulus, and this is because of numerical errors. So if we increase the modulus too much, then polynomial multiplication will be a little bit noisy. So there'll be these numerical errors, and if it's too big, then these numerical errors are too big, and our computation is no longer correct. And you can see the consequence of this in the last two columns. So for FFT, we need to compute more multiplications. Then the largest difference between my scheme and the S16 is that I need always one bootstrap, whereas the S16 needs 5 or even 10 to sanitize a ciphertext. But let's go quickly back here to the differences in implementations. So remind that we need a prime modulus for NTT implementation, but for FFT, we can actually choose whatever modulus we want. Given that it's smaller, for example, we can choose a power of 2 modulus. And this has some actually pretty interesting consequences. Okay, so remind you that we need to implement this randomized decomposition algorithm. So I implemented 2 algorithms, both from a paper by Janice and Michancio. And don't worry, I'm not gonna go into the details of these algorithms, but I just want to showcase what is the visual complexity of both algorithms. So the algorithm on the left, it's specialized to a special moduli that are of the form b to the k for some base b, for some k. So for example, it can be a power of 2, and this is what we are using in the fast Fourier transform based implementation. So it's very nice and very simple. But then there is the decomposition algorithm on the right, and that works for every moduli, for instance, a prime modulus, and this one is used in the number theoretic transform implementation. And later in the experiments, you'll actually see the difference in the efficiency impact that these algorithms have. So, but roughly, to summarize both implementations, we have this. So the NTT can have a larger modulus, but you have to do more expensive modulus reductions, whereas with FFT, the modulus reduction is for free if it's a power of 2. But the modulus needs to be smaller due to limits on precision and numerical errors. Then for NTT, randomized decomposition is quite complex, whereas for FFT, it's actually very simple. Okay, now the first table you already saw. The second table gives you finally some timings. So deterministic computation is the same in mine and the S16. So I intentionally chose the parameters like this, so that we mostly focus on comparing simulation mode. And the biggest differences in deterministic mode really between the implementations. For FFT, it's actually slower, and this was quite a surprise to me at least. But on the other hand, we perform more polynomial multiplications for FFT due to smaller modulus. So perhaps that's the reason why it turned out to be slower. Then to sanitize the error, we just need 1.44 seconds for NTT and 1.22 seconds for FFT. So you can see that the randomized decomposition in NTT implementation takes around 80% of the entire execution time, where for FFT it's just around 40% of the entire execution time. So that's why sanitization in the fast Fourier transform based implementation is much faster. So in both implementations, sanitization for DS16 is slower because we need to repeat bootstrapping for 5 or 10 times. And finally, let me just note that the implementation of the randomized decomposition is currently rather straightforward. So it can actually be very nicely parallelized and speed up by, let's say, like using AVX instructions and so on. So I think that there's still much room for practical improvement. And like looking at the numbers, so I think that sanitization in both cases can be done below 1 second. But for the S16, there is actually not much improvement that we could do. So aside of improving bootstrapping algorithms themselves, but this improves both sanitization methods. So it seems that in practice my method performs a little bit better. Okay, so to summarize, all the algorithms are implemented in a library that I call FHE-Deck, and so the library supports various flavors of functional bootstrapping or programmable bootstrapping, if you prefer. All parameters are chosen to support circuit privacy. Plus, there are estimator scripts to help you come up with new parameters in case you need to meet some specific requirements. So here is a short example of a C++ program that computes the ReLU function. So first we encrypt some numbers, then we can define a lambda expression that specifies the function we want to compute, and we simply run eval loot on it, and it works. But most importantly, so if we want to send a ciphertext to a file, or let's say a network socket, then it automatically sanitizes the ciphertext. You don't need to think about it. And of course, so you can also call the sanitization algorithm explicitly. And there are also possibilities to store ciphertext without sanitization, if for some reason you would like to do this. But it's hidden below the interface, so we have to put a little bit more work into this. And finally, so what you see here is the upcoming version of the library. So I'm cleaning now the repo a little, and I plan to release the new version somehow next week, unless some unexpected things happen. You never know. And this wraps it up. So thank you again for inviting me. You can invite me again anytime, and I'm happy to take questions.
Thank you, Kamil, so much.
Yeah.
We'll start with the questions that were mentioned in the chat during the presentation. Siva had asked, what's universal circuit?
Yeah, so a universal circuit, so this is a circuit that takes as input another circuit, and your input, and outputs this other circuit evaluated on your input. So yes, so you can think of it as a program that evaluates another program as an input. So this is in short. And so why let's say in garbled circuits, why it hides the topology is that okay, so and even simpler. So if you are familiar with neural networks, so you can think of a universal neural network as a neural network that has its like parameters. No, okay, maybe it's not the best idea. No, okay, this is not a good example of the neural network. No, okay, so to summarize, so it is a circuit that takes as input another circuit, a function, yes, and an input that outputs this function evaluated on the input. Okay. I hope it clarifies. If it doesn't clarify, then let me know.
Great. The next question, Siva, did you want to go ahead and do it over voice, or? Okay, so the next question was, what about circuit privacy for leveled homomorphic encryption schemes? They asked, if they're not wrong, the circuit privacy you achieved by doing randomized bootstrapping is for public keys. What about the circuit privacy for symmetric key FHE?
Okay. Yeah, I mean, yeah. If you have homomorphic encryption, or at least LWE homomorphic based on homomorphic encryption in the symmetric key setting, yes, then you automatically have FHE in the public key setting. Yeah, so you just publish a bunch of ciphertexts of 0, you do a multi-sum, and you get a fresh ciphertext, yes, and then you just add your message that you want to encrypt. Yeah, so you get public keys like basically immediately, and yeah, so you can treat my scheme, yeah, also, yeah, as a like valid candidate, yeah, for symmetric key FHE. But so there's also a part of the question: what about leveled homomorphic schemes? Yes, yeah, so there are schemes like this BGB, BFB style schemes. And these are, I think, implemented in, for example, IBM HELIP or Microsoft Seal. And there, the parameters are often already so big. Yes, so the dimensions of the rings they are using and the moduli, yeah, are already so big that choosing this very big flooding noise becomes an option. So yeah, so there. Okay, well, given that the computation that they do is not too deep, yeah, because so the flooding noise also depends on how deep you compute it and so on. Yeah, so there you could actually use flooding. And I think that in some applications, yeah, they actually do it. Yeah, they flood the noise. Yeah. However, yes. So of course you can use this scheme here, yeah, to also sanitize the ciphertext, yeah, from this leveled homomorphic encryption schemes. Yeah. So what you do, you just switch from one scheme to another, and you are done. Yeah, and you can run sanitization. Okay.
Okay, thank you for that. So that ends the questions that were queued. I'd like to open it up to impromptu questions from everyone participating. Just a reminder, we're a community. There are no questions too big or too small. So everybody feel free to ask whatever comes to mind. Don't be shy.
I'm familiar with universal language.
So if anyone has any questions, they can just jump right in and ask.
Yeah. So maybe along the way, so Siva says that he or she is familiar with universal Turing machines. Yes. So yeah. So the universal circuit, yes, it's something like a universal Turing machine. Yeah. So except so in a universal Turing machine, yeah, you take a tape, yes, with the program, yes, and a tape, yeah, with a message, yes, and then you the universal Turing machine evaluates the program, yeah, on the message, yes. With a circuit, with universal circuit is similar, yes, except so just switch Turing machine, yes, to circuits, yeah, and you get roughly the same thing. Is CKKS circuit private? Yeah. Okay, that's yeah, that's a really long question to answer. Yes. So in short, so there is this paper, yeah, that we put on ePrint recently. So on circuit private, multi-key and threshold approximate homomorphic encryption, and there we look into circuit privacy for CKKS and so on. Yeah. So okay, so from this talk, yeah, remember, yeah, that so the definition of circuit privacy required us, yeah, to have correct computation. Yeah. So CKKS, yeah, already by definition is not correct; it's approximate. So yeah. So first thing, yeah, we had to do is we had to give a meaningful definition, yeah, for circuit privacy in this case. Okay. In short, yeah. So we redefined secret privacy, and instead of like the simulation-based definition, yes, where you have to get, so the simulator has to get an evaluation of a function. So we ask whether it is possible to distinguish, yes, between evaluating one circuit and evaluating a different circuit, given that the circuit evaluates to exactly the same message, yeah. Okay, and yeah, so it is possible, yeah, to come up with some circuit private CKKS, like a circuit private CKKS scheme, yeah, that like satisfies some notion of circuit privacy. Okay.
Great, thank you so much.
Yeah.
So we'll give a minute for anyone else who had additional questions, and if no one comes up with any in the minute, we'll go ahead and conclude. But let's see if anyone comes.
Yeah.
Okay, then. Thank you so much, Kamil, for presenting. For everyone in the community, the resources from this meetup will be on the website soon, and we much appreciate you coming and taking the time to present to us.
Yeah, thanks again. Yes, and yeah. So one last thing is that next week or next 2 weeks, I should update the paper actually. Yeah.
Excellent.
I think that there were some typos and so on, yeah, and some parts of the proof can be actually simplified. Yeah. So I guess I'll update this. The library plus some at least smaller documentation should also appear somehow next week, I hope. Yes, it's a lot of work. Yeah, so I hope I'll do this. And yeah, so if you have some future questions, then Eta on the Discord, yes, or send me an email.
Awesome, thank you so much.
Thanks again for having me, and yeah, you need new talks, then let me know.
Thank you, and thank you for everyone for participating today. Everyone have a good week.
Bye.